Good afternoon. Okay, so last time the material from Friday was linked lists and how they are different from vectors. So again, just recall with a vector, it's very much like a stack of books. So you can put a new book on top, you can take a book off. Those are easy operations to do, but for if you want to remove or insert an element in the middle, that's a little bit more computationally intensive. With a linked list, on the other hand, with a vector, right, if you want to find the 2 billionth and 6th element, you know if you know where the first element is, you know exactly in memory where that particular element is. That's a property called random access memory, or that's called the random access property, which sounds a little weird because it sounds like it's random, but it's not. What it means is you can pick any point you want, any index you want at random or whatever, doesn't matter. It will always know exactly where that element lies. This is as opposed to linked lists, right? Where a linked list, you know where the first one is, and sometimes you know where the last one is, and you really just have to go one by one. If you want to find an element, you literally have to go one by one. If you want the 5 billionth element, you have to start at 1 and traverse through all 5 billion elements to figure out exactly where you need to be. Okay? On the other hand, if you're in the middle of the list and you say, hey, I want to insert something here, I'm sure as you guys all saw on Friday, it's easy to just kind of piece something together. If you're in a vector, not as easy. So today we're going to study a little more abstract concept that's called stacks and queues, and we'll see how they compare with linked lists and vectors. So again, that's just to summarize. Last time, vectors only let you pop back and push back easily, and inserting elements in the middle is cumbersome. Linked lists are easier to insert and erase, but accessing particular elements involves iterating through all previous elements. Okay, so there's also a little difference between singly linked list and doubly linked list. And again, it's really more of a what do you plan to do with this collection of objects. If you want to do, by default, a singly linked list, that's kind of the bare minimum structure you need to have. You start at the first element, and it just needs to know how to get to the next element. Sometimes, though, with algorithms, you want to be able to backtrack a few elements, like you want to go forward, and then maybe you want to go backwards a little bit, or you want to go to the end and go back one, or things like that. Then you need what's called a doubly linked list, and that requires a little more memory, right? Because instead of just having pointers to the next element, you also need a link going backwards as well. So if you don't need to go backwards at all, it's actually more efficient not to have the links there in the first place. But if you need them, C++ 11 especially gives you a very easy ability to go both forwards and backwards. It gives you these built-in data structures which have all these operations defined. Okay? Another reason why you might want a doubly linked list is because if you're going to be accessing the first part of the list a lot and also the last part of the list a lot, it allows you to just start from the back and go forward than to keep going each time from the beginning. Okay, so if you're going to create your own linked list or write your own code, the most basic form of error checking are what are called assert statements. And all these assert statements do is check to see if a condition is satisfied. It's like an if statement, except if the condition is false, then it causes a runtime error, and the entire program halts. This is great for debug purposes, but when you're in a production environment, you don't just want your program to crash and stop. On the other hand, at this stage, it's probably not I'm going to hold off on error checking altogether. So this is the most basic form of error checking, which can help you, while the program is running, figure out exactly where something may have gone wrong. So it's a great debug tool, but when you go to release software into the world, as a matter of fact, assert statements actually get ignored. Okay, so assert is a way to cause a runtime error while your code is running, but only when you're in debug mode. Okay? When you go to release mode, it implies a more kind of professional environment, and the assert statements all just disappear. Okay? But as long as we're in debug mode, they help let us know where our program went wrong. Okay, so now just quick, let's see. All right, so again, if you actually create your own node class, you're going to have basically some data like a string or an int or a double, some container containing or some data type which contains the values. You're going to need a node pointer to the next object and a node pointer to the previous object. Okay? So the idea of a linked list is universal. It doesn't matter what language you're in. That idea is the same. The idea of a stack of books, that's the same. In C++, though, we would implement the links using pointers. Okay? So you have a node class, and each node is going to have a value, and it's also going to have a pointer to its neighbor in the next. And for a doubly linked list, it's also going to have a pointer to the node previous. Note that it's not a pointer to the value of the previous node, like the string property. It's a pointer to the class object itself, a node type. It's kind of weird, though, too, right? Because you have a node class, and within that node class, it has a node pointer type as a member. But it works. Okay, so in cases when the node is the first element in a list, the pointer to the previous object is set to null PTR. Did I give you guys the null PTR speech yet? I'm seeing a lot of that, a lot of both. Okay, basically, wherever you see null, you should replace with null PTR. At a later date, I may explain the subtle differences between them. It is much better to just use null PTR, all lowercase, than capital N, capitals N-U-L-L. Okay? So in general, in your book, when you see N-U-L-L, just replace it with null PTR. That's a new C++ 11 thing, but it's definitely one where I can very easily say, literally just replace all instances with N-U-L-L PTR. There we go. Okay. Now you're going to have a list class, which is going to contain two private variables, and then you're going to have it's going to point to the first element and point to the last element. And then the iterator class is going to have two private variables. It's going to point to a particular node, and then it's going to be aware of what list it's currently in as well. Okay? So especially if you erase or insert a node at the front or the end, you need to be able to communicate with the list object itself, and you just need to be aware of what container you're currently in. So this is really more what I want to focus on, is looking at the actual code. Okay, so your node is like the actual data itself, but it's not just about the data, it's about the data and the links connecting the data to another set of data. Okay, so here we've got string data. I'm implementing it using a string. And then we have pointers to the previous node and the next node. Now I'm also making list and iterator classes friends because presumably all three of these classes are working together and they were all written by the same person. Okay, so that's the idea behind this, in that there's a lot of operations which you could get around not having friendship, but it makes sense in this case to put it in there because there is a cohesion between these three classes. Okay? These are not meant to be defined and worked with disjointly or separately. These are, in fact, meant to be worked with in the same kind of space. Okay? And just note that you can replace the string property with fraction, polynomial, I mean, you can replace it with anything you want, and everything should work exactly the same. Okay? There's nothing special about string. Here is the implementation for our actual list class itself. So notice the two private variables are a pointer to the first element and a pointer to the last. And make sure that when you're iterating through the elements in a list, you are able to detect when, in fact, you are coming to the end of it. Or if you want to start in the beginning, well, not even that. It's more like if you want to search for something, you start at the first node, and then that node knows how to get to the next ones. Or you start at the end, and then that node knows how to go backwards. Simple as that. But that's pretty much it. The list class, and this is important, okay? The list class just needs to know where the first and last elements are. After that, each node itself knows how to get to its neighbor, and so all of the nodes are therefore connected. Okay? So the list class itself only really needs to know where the first and last nodes are. And then finally, the iterator class. The iterator class is going to act and feel like a pointer. Okay? It's going to really have a lot of the characteristics of a pointer. But it's not itself a pointer. It is a class, and it contains a pointer to a current position. It also contains a pointer to the container it lies in. Okay? And then, again, it's working together with the other classes. Okay? So it is not itself a pointer, but it is a class which is designed to mimic a pointer. And in particular, if you look at that property get, if we want our iterator to act like a pointer, rather than having a function called get, which say returns the value of the string in the node from position, we could overload the operator star. And then we can start to, we have a class, which is a class object, but we want it to feel exactly like a pointer. We can start overloading some of the usual operations on pointers if we want. Okay? Yeah, question?
Is there like a special significance for putting the friend class list in the private section of your class?
Very good question. And I had to look this up a little bit ago, which is, I didn't know the answer to this, which is this location of friend class list. Is there a reason why it's in the private section of the class? Is that intentional? And the answer is it doesn't actually matter where you put it. It does not matter where you put the friend class declaration. What I've seen a lot of times is because it doesn't matter, I've seen all of the friend statements at the top of the class. So right after the line class iterator, the next line down, without a public or private before you've declared that, it just lists them, all the friendship relations. And by default, that's in which section? In the private section, but it doesn't matter one way or the other. And I did look this up in the standard. I looked this up because I wasn't 100% sure. And the standard says, friendship does not matter if it's in the private or the public. So yeah, that's going to the C++ standard is kind of like saying like, well, what does the law say about this particular issue? And then like reading it and be like, okay, it very explicitly states it doesn't matter. So very good question. I didn't know the answer until very recently. Okay. All right. So we get the idea of a linked list. We've sort of been dealing with them for the last couple lectures. Now let's move on to some of the other data types you can work with in C++. So, and in general. So the vector data type is a particular example of what's called a stack data structure. Okay? A stack is to be thought of as a pile of books that you can take from the top off, or you can put a book on the top of the stack. But accessing middle elements is not feasible. Okay? That's the idea. The std::, vector data type, the vector from the standard library, is a particular implementation of the idea of a stack. Okay? It is a very good one. It's very fast. It's very optimized. But it is, in fact, from that paradigm. Okay? This is why with a vector, one of the first operations you learn on in a vector in Pic 10a is pushback and popback. And you might say to yourself, well, that seems a little odd that we would only be able to add to the end and take off from the end. I mean, in general, we would think of just like maybe in a library, maybe a bunch of books, and we go to the middle, we take a book out from the middle, we read it, we put it back, or we put it on the shelf because they want to be able to put it back in the right order, okay, something like that. All right, but there's not this restriction in our minds a lot of times that we can only work on the end anymore. You wouldn't, to access this book, you wouldn't, in a library bookshelf, you wouldn't like take out all the books before it, take it out, and then put them all back. Okay? Oh yeah, there's this story here. Okay, well, okay, there used to be arcades. Do you still use quarters, or do they do cards now or something? I don't know. At one point, they tried to switch people over to like in an arcade, like having like a card you put in, and I think that failed. But when I was a kid, I remember one time I got this like coin holder, so it like clipped onto your like this clip of the microphone, it clipped onto your belt or whatever, and you just put a bunch of quarters in the thing, and if you needed quarters, you just, with your hand, you just go, toot, 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 you just kind of pop them out. And so that's the idea of a stack, is, okay, you push them in, the first one you push in is the last one that gets popped out. It's that idea. Oh, it's also like a Pez dispenser. Okay, yeah. Okay, so here's an example of, in fact, maybe you knew this or did not know this, there's an actual stack data type in C++. Not even C++11. This has been in there for a while. Okay, C++, pre-C++ 11, provides the most basic form of stack data structure you can possibly imagine. Vector is a souped-up, really nice version of this stack, but sometimes you may not want to include all the bells and whistles, and you just want to access the very basic structure. This is it right here. Okay, so you have a stack of strings. This is just like vector of string. It's the same idea. Different data type, but same idea. You can push, not push back, but push Tom, Dick, Harry onto the stack, variable S, and then you can print out each one in the order in which they get popped off the stack. Okay, so you have a s.top. Top gets the element on the top of the stack. S.pop pops that element out. It's just like saying, for example, S like v of v dot size minus 1, for example, and then doing v dot pushback. Same idea. And then this prints out Harry, Dick, Tom. Okay, in reverse order of the order in which you've inserted them. This is what's called LIFO, last in, first out. In other words, the last one that got pushed in is the first one that gets pushed out or popped out. If you think of maybe a really skinny elevator, and you all kind of walk in the elevator, and then you turn around, and then whoever was the last one in the elevator, well, they have to get out in order to let the other people out. Okay, maybe skinny elevators are not great examples. All right. Don't think about employment. That one I don't think. Maybe it's relevant. I don't know. Longest serving employees get seniority. The first ones to go are the recent additions. I don't even know if that's realistic. Okay. Now this is different from lines or queues. Okay. Think of grocery store. Think of Department of Motor Vehicles. Don't get depressed. All right. Just any kind of line where you go in the line, and the order in which you entered the line is the order in which you get serviced. Okay? First in, first to come out. All right? That's the idea. So this is your classic formation of a line where the order of appearance matters tremendously. Okay? In other words, you want people arriving earliest to get served first. First in the line is the first one out. As opposed to the stack, which is the first one onto the stack, is the last one to get popped off. Now for this, you have almost the exact same implementation. Okay? If you want to add these strings to the queue, it's called a queue because that's the British form of the word line. I guess queue sounded better, probably. Also in probability, queue actually is usually the usual term that they use. So it's a very standard technical term. It probably just sounds better than a line. I don't know. But queue is the data type. It's the actual data type in C++ is what it's called. Okay, that implements this structure. So we create a variable called q, a variable of type q with variable named k. Now, does anyone know why I named the variable k? So I could write K-pop. Okay, now that you're awake, all right, so remember. So everything is going to look very similar, except we're working with a different data structure. We are organizing the collection in a slightly different way. So when we push in Tom, Dick, and Harry, while the size of the collection is positive, we're going to print out k.front. right? Front is mnemonic for the line, the front of the line. Top is mnemonic for the top of a stack of books, okay? So that's where these words come from. K dot front prints out the first element, and then K dot pop pops out or just services the first one that was in there, and then the other ones in the queue move up, and then we loop through until all of them are popped out, and then this will print Tom, Dick, Harry in precisely the same order in which they were inserted in the line. And that's ideal, right? You want to service people in precisely the same order in which they were added to your queue. Question?
So queues and stacks, is there, you can only access the first element in the queue? There's no other method for anything else?
So the answer is for queues and stacks, you can really only access the first element. You can also access the last element. Yeah, you can access the ends. So the particular implementation of queues and stack classes in C++, the answer is yes. You can only access the first element or the last element. This is because they're designed to be the most minimal application of this idea. You could create your own class which gives you that random access property if you wanted. There's a danger to that, though, because, well, let me just leave it at that. Yeah. This represents just the bare minimum set of functionality for queues and stacks. Yeah. By bare minimum, I mean bare minimum. This is pretty much it. These are all of the member functions provided for you by the standard library stack class. Okay? So if you ever tried at one point to try and memorize all the different things you can do with a vector, like vector.size, vector. There's a huge long list of member functions associated with vectors. For stacks and queues, that's it. That's pretty much it. Okay? So you start with the ones for stack. You can test whether it's empty. You can return the size. You can return what you get as a reference to the top of the stack. So you get what gets returned is the actual object itself on the stack. You can push and you can pop. You can't even get the bottom of the stack. You can only get the top. Okay? With a queue, it's the same idea, except you're pushing and the order you push in is the order which you pop out. Same as above, except replace top with front and back. Okay, so with the queue, you can access the front of the line and the back of the line. Which makes sense because if the front of the line gets popped off, you need to be able to get to that, access the front of the line, pop it off. If you push somebody on, you need to be able to access the back of the line so you can make sure everything gets added correctly. Question?
Why would we use the stack? Why don't we just use the queue?
No. Okay, so good question. The stack and queue store the elements inherently differently. They allow you to access and pop off elements inherently differently. Okay? If you want to design a system around, let's say it's like a grocery store, right? And every time a person enters a line, you want to create a customer object and push that customer object into this queue. You don't want to encode that as a stack because you want the customers in the line serviced in the order in which they arrived. You want to add them to the queue and pop them off. So it's a design question. Now, the better usual question is, why would you use a stack? Why not just use a vector? You would use a vector for everything. You would never use a stack. Okay? But it exists in the standard library, and it's there to say, well, if you didn't want anything else, that's the bare minimum concept. Okay? That has nothing to do with C++. The idea of a stack, the idea of a queue, nothing to do with C++. But they have an implementation in the standard library. Okay? So it has everything to do with how your collection of objects is going to be added to the collection and removed from the collection. If they need to be removed in precisely the order in which they entered, you want to use a queue, because otherwise there's more shuffling around. Yeah. Question?
Internally, would you say the stack and the queue, would they be implemented like a linked list, because you're not really having the random access stuff? Like, is it, in that sense, more?
It's a good question. I don't know off the top of my head how they're actually implemented in the standard library. I know how other containers are implemented in the standard library, but nobody uses stack and queue as far as I can tell. They use the idea of them, which is why the idea is what's mainly important. But the actual, how they're implemented, I believe the stack is implemented using a vector by default. And then actually, I think the queue is implemented using a double-ended queue. By default. And then we go down a path which is really customizable, which I won't go through right now. But yes, they are implemented by default in a certain way. And here's the cool thing. You can actually implement them using a linked list, using a vector, you can create your own container with which to store the elements, as long as it satisfies certain properties that's demanded of a container type. So this is getting into a level of detail that you don't need to know for 10b. But yeah, it's highly customizable. How you actually implement them is very customizable. OK, I wanted to get through that lecture so that we can move on to lecture 19, which is a little more fun, on sets. Sets. We've already seen this idea, which is storing a collection of objects. I have a set of objects. I want to store them in the computer in some organized fashion. And how I choose to store them depends on how I want to add to the list and take away from the list. If I want to add and erase from the middle of a list or a collection of objects, I probably want a linked list. If I want to randomly access particular elements really fast, and I can store them all contiguously or consecutively in memory, I probably want a vector. I want a stack data type, but by default, if you want a stack, you're going to use vector. Vector is really optimized. I want to highly encourage you all to always use vector by default, unless the particular application compels you to use a different data structure. Okay? Here's an example of how you might feel compelled to use a different data structure, which is, okay? So sometimes you really don't care about the order or duplicate values stored in your collection of objects. Okay? If I want to store the number as a bunch of ints, and maybe I have the number 5 showing up 7 times, maybe I don't care how many times it shows up, I just want to store the number 5 in my collection and ignore all other attempts to insert more 5s. Okay? That's the idea behind a set. Okay? Now, you can do some pretty weird things with sets. We're not going to have to think about any of those things. But the the foundation of mathematics, there's a set theory, axiomatic set theory lays a foundation for a lot of mathematics. We don't need any of that. There's some subtleties that you could go down and go crazy thinking about. We're just going to use the most basic intuitive notions of sets. Okay? So what is a set? It's just a collection of distinct objects considered as an object in its own right. Forget about considered as an object in its own right. It's just a collection of distinct objects. And then from your book, I think it says a set is a gathering together into a whole of, no, that's also from Wikipedia. Georg Cantor says, a set is a gathering together into a whole of definite distinct objects of our perception and of our thought, which are called elements of the set. It's very deep. Okay. And your book says, in mathematics and computer science, an unordered collection of distinct items is called the set. These are the two important characteristics. Okay? They're unordered, meaning if I have elements 1 and 5 in my collection, I don't care if the 1 comes before the 5 or where they're actually located in my set. I just care about the idea of a 1 or the idea of a 5 being in there. In particular, they are all distinct as well. I don't have 2 1s in my collection. If I try to add another 1, I just want to ignore it. Those are the 2 main properties. Well, there's a class for that. Okay, so there's actually a container called set. There's a class definition for set, and it works exactly the same as vector, stack, queue, all the other standard library containers. They're called containers because they contain a collection of objects. It just has a slightly different interface, and it does slightly different things because it stores the collection of objects in a slightly different way. Okay? So again, this is, if we don't want to include duplicates, we don't want to insert the 5 there, right? The 5 and the 7. Now, we could put all these things in a vector and do a manual test to say, okay, if the 5 is already in the vector, don't insert it or don't push it back. But that's cumbersome. We don't want to have to think about that when we're writing code. We want that type of detail to already be taken care of for us. And this set class does that for us. Okay? So the idea here is you can ignore, I'm going to rewrite this gobbledygook. We want to insert a bunch of elements, and then we want to print them out. So let me show you what you can do. You can take this set of code. Well, let's just do from main. Now watch this. You know how I keep telling you guys about C++11, and I'm like obsessed with the C++11 thing? Yeah, I see some heads nodding. You're obsessed with C++11. Yes, I am, and I'll tell you why. Okay, so let's include set. Not all magically compiles. Let's print this, or let's run this, and it prints out all of my elements using that code right there, 1, 3, 5, 7, 12. And notice there's no duplicates. Everything is distinct. But what else do you notice? What else do you notice about how it printed them out? It's in order. Even though the order doesn't matter, it still printed them out in order. That's this thing, okay? If you want to store a set of objects, say of data type int, you have to be able to compare them and find the one that's less. You have to be able to compare them each pairwise. Okay? I'm going to replace that code right there. I'm excited. Watch this, guys. Watch this. Okay. This is why C++11 is so, it addresses a problem that they were having more than 10 years ago, and other languages like Python and those other ones tried to address it earlier, and now they finally got it working nicely. Watch this. Watch this. Okay. Ta-da. Okay. Wait, have you guys seen this before? Yeah, what did I do? Where did you see this before? Printing out all the elements of a vector. It magically works for all of the standard library containers. You can even define your own classes, and as long as you overload certain operators, this will also work for your custom-defined collections of objects. Okay? That's what's so cool about C++11. Tell your friends. Okay? So the idea here is the focus of what we want to do is not about iterators. It's not about how the set stores the elements. We want to focus primarily on the idea behind a set as a data structure. And this code here really distracts us from really just communicating the idea of how do the elements that we try to insert get printed out. And we use the exact same code whether or not this was a set or a vector or a list or any other standard library container. Okay? That's why C++11 is really it's really nice added set of features to the language. Okay? It pretty much addresses all the concerns that a lot of other languages came into existence over. Okay? Okay. I will try and contain my excitement in the future. Okay. Actually, no, I won't. I will continue to express my extreme excitement for the new features of this language because really, I'll show you how the magic happens. So make a copy of that, and then I can replace this with this. I can do something like this. I can write in the comments, C++11 rocks. Okay, I change that to that, change that to blue. auto goes to blue. This goes to red. And now, okay, next time I teach this course, for example, I've got the slides, and I say, oh, or in C++11, you replace it like this. Okay? This is also how languages develop over years and years as well. They go to a point like this, and they say, that's ugly, I don't want to write that code. Is there anything better we can do, any feature we could add in, any way to modify the syntax of the language to make programming more accessible to a larger set of audience? Boom, there's your answer. And the reason this rocks even more than usual is because this is the exact same syntax no matter what the type of container is. Okay? That's where programming languages are going, to this idea of a generic programming. In other words, I do the same thing. I call the same function, I write the same code, and it doesn't matter how the actual elements are implemented. Okay? Let's see. Okay, so objects stored in a set are actually ordered according to the less than operator. So if you're going to store a set of 0.2Ds, for example, you have to have the operator less than overloaded on them, otherwise set won't work. Well, you can create a set of that type, but you can't insert any elements into it. Okay? So it will store the numbers in a particular order, because the order doesn't matter, but we need an order ring in order to store them properly. Okay? It will also disregard attempts to include duplicate entries. Okay, so like we saw, here when we try to insert the 5 and the 7, if we're working with a vector, sure, we can test for that, but we don't want to test for that. You know, we want it to automatically get taken care of for us. That's what that does. Okay, so I want to introduce some of this very common mathematical notation and idea. Probably if you took a very basic level math course or even in high school, you've seen this before. Let's just review it to then connect it with the member functions and the operations for the set container in C++. Okay? So sets are fundamental mathematical objects with few well-defined operations. For example, if you take the union, you just take the collection of all elements in both sets, and you just disregard duplicates. So here, the 1 is duplicated. 1 is in both A and B, but it doesn't matter. Just 1 appears in A union B, and you just take the set of all of them. Intersection is the set of all objects that are in both A and B. So for example, the intersection here is just the numbers 1 and 5, because those are the only elements which appear in both sets. There's also a set difference, which is, now set difference is a non-symmetric relation. The order here definitely does matter. Okay? So what we have is A set minus B is all the elements in A that are not in B. That's how you can think about it in words. So A without B is you take all the elements in A and you just take out the ones that you see in B, and then you can reverse that. Symmetric difference is one you can say in words. It's all objects that appear in one of A or B, but not both. So they have to either appear just in A or just in B, but not in the intersection. So another way to write this is you take the set difference and you just union the two set differences. Or another way to write that is that there. You don't need to know this stuff. Okay? You just need to know the idea of it in order to connect it with the idea of how the set is implemented. Okay? The size of a set is just the number of elements in the set, and it's usually denoted by absolute values around the set. So for example, 135 with absolute values around it just means the size, or 3. And okay, that's pretty obvious. So can a set have size 0? Yeah, it can have size 0. It's just a set with no elements. This is what's really cool. There is a C++ analog of the empty set, okay, for a set object, and that's why we'll get to that in a second. So there is a set called the empty set, usually denoted by the circle with a line through it or open-closed brackets. It has no elements. Its size is 0. This is a very perplexing set for a lot of people, because is it like what? I mean, it's a set, but it contains no elements. So is it a thing? Does it actually exist, or are we just talking abstractions here? It's an actual thing, okay? It is the empty set. It is the set with no elements in it. Okay? That will have a very concrete meaning in C++, as we'll see in a minute, okay? So another thing is a set can contain the empty set. So for example, if A is the set which contains as its only member the empty set, that is a perfectly fine idea. Okay? The empty set is a perfectly concrete idea. You can have a set which contains that set. Okay? You can continue this line of thought, and I was trying to be a little cute here when I wrote these slides initially, but basically if you let B be the set of all previous sets that you've seen, it's the empty set and the set with the empty set, and you let C be the set of all sets you've seen before, which is that one, and then that one, and then D be the ones you basically, if you look at the sizes of those sets, the size of the empty set is 0. What is the size of A? 1. What is the size of B? What is the size of C? 3, 4, et cetera, et cetera. So we've kind of defined the natural numbers. Okay? So that's a cute little way to define what the natural numbers actually mean. You don't have to know about it for this class, but it's a cute little thing to connect it with the material. Congrats. All right. The power set is one that's a little more computationally intensive in general. If an algorithm involves computing all subsets of a certain set and then doing something on that, that's a very slow, impractical algorithm, unless set sizes are very small. But we denote it by 2 to the power of A. So for example, when A is 159, the set of all subsets includes the empty set and the original set as well. And then it includes all possible ways of taking 1-element subsets, 2-element subsets, it's all the way up to the size of A. Okay? The reason why it's usually denoted by 2 to the power of the set A is because the size of the power set is 2 to the size of A. Okay? So the size of 2 to the A is 8 because the size of A is 3. Okay? Now, the power set in general, in a mathy sort of sense, maps a set and it creates another set. But in C++ land, for example, we have a very specific input and a very specific output. So if we input the set of all sets of elements of a set of ints, what we get is a set of ints. Okay, so just think of the example above. Our input is a set of ints, say, with elements 1, 5, 9. The 2 to the A is a set of ints. Each element in the 2 to the A is a set consisting of a certain number of objects. Okay? So again, it's a subtle difference in the idea and the practical implementation of that idea. Then there's the idea of a complement. A complement is the following idea. Take this set and just take everything except for that set. And usually the question is, what do you mean by everything except that set? Like, what's the complement of 1, 2, 3, 4, 5? Is it all numbers except 1, 2, 3, 4, 5? Is it all integers except 1, 2, 3, 4, 5? Is it the entire set of all possible sets of everything except the set 1, 2, 3, 4, 5? Like, what does that mean? So typically what we have is the complement means, take the complement of 1, 2, 3, 4, 5 with respect to this fixed larger set. And then it just means, okay, take this larger set and take everything and then just subtract out the set of interest. Okay? So we denote this by a to the power of little c. So if you have basically a larger space denoted by omega, which is the numbers 1 through 9, and a is 1, 3, 5, 7, 9, the odd numbers, then the complement is just the even numbers, which are strictly less than 10. Okay? So it has to be complemented with respect to a explicitly defined larger set. I remember I got asked once, how do the set operations work with the empty set? So that's what this slide addresses. If you try and call union with the set, any set A, you just get A back. If you try and intersect any set A with the empty set, you just get the empty set. A set minus the empty set gives you just A. Empty set minus A gives you the empty set. And then the symmetric difference is maybe the little weird one to think about. But you just follow the formula from the previous slide, and you just get A back. All right, now I'm excited. All right, guys, now pay attention. Wake up. All right, here we go. Let's connect this now with programming. Okay, so we already have an intuitive notion of how set operations work. We've seen this before. Okay, but maybe this set class we haven't really thought of, or we want to connect it. Now, when you create set of ints called mySet, how many elements does the variable mySet have initially? 0. So what kind of set is it? Empty set. We've created the empty set. Just by creating a variable, we've created the empty set. Now, when I call .insert, what type of operation does that apply to my set? Union. Okay? And that's what we want, because if we apply the union operation, when we go to do duplicates, when you union a set with an element that's already in the set, what does it do to that set? Nothing. It just stays the same. Okay, so that's how you can, and when we call erase is just doing a set minus operation. If we call set minus on a set that doesn't have the element, nothing changes. Okay? So this is to help connect with you this very intuitive notion you've already seen before in a previous setting. And if you haven't, we reviewed all of it regardless. Okay? To now, all right, an actual programming kind of idea, how it's implemented, this is precisely how it's implemented. Calling insert really just takes the union, which is why it's insensitive to duplicates. Calling erase is the same thing as calling set minus. This is why you can call erase on an element that's not in the set, because it doesn't matter. It's still just the same set it was before the call to the erase function. But in particular, the really cool thing is that this A is the empty set. When you create the variable, you create initially the empty set. So it has a very abstract meaning, but it has a very concrete meaning as well, as is shown there. Okay, I'll end with this idea, which is, I had you do a homework assignment with integer partitions, right? That was one of the combinatorial sequences I had you work with. An integer partition is not a collection of distinct elements where order doesn't matter. An integer partition is a collection of objects where order doesn't matter, but multiplicities do. So in a set, we wouldn't have 2 7s or a bunch of 1s. But in what's called a multiset, still the order doesn't matter, but we keep track of the number of each type of element. Okay? So that's the more general type of idea, which is, okay, at a bare minimum, you have a collection of distinct objects, and the order doesn't matter. One step up from that is I have a collection of objects. Duplicates do matter, but then the order doesn't matter. Okay? So we'll start with this example on Wednesday.